Hi there. So right now we're going to be looking at chapter 22, which is electromagnetism. And this chapter is split into four parts, which is force on a current conducting carrying wire, which is what we're doing today. And the other two is force on a moving charge, magnetic fields due to currents, and force between current carrying conductors. But today let's focus on current carrying conductors. I wanted you to carry through a core concept first before we begin. Basically, there are three fundamental aspects to or everything to do with kind of magnetism in general, and all the questions we'll do, at least in the Cambridge syllabus. So, if I just draw three circles here, so I can kind of visualize this idea to you. So if I put here on the red circle, magnetism, and in the orange circle, I'm going to put motion, and in the yellow circle, I'm going to put current. Okay, so the idea is, if you have any two of these, it will cause the other one to occur. And I'm just going to draw a little magnet here so you can kind of visualize what's happening. So here's my magnet, and in between I'm going to put a wire, and I'm going to, so if this is the north pole, and that's my south pole, I'll be able to draw field lines across. So there's a wire in a magnetic field, and this is basically the basis for all magnetic activities. You normally have some kind of wire or some kind of conductor inside a magnetic field. So let me explain. If I have a current carrying conductor inside a magnetic field, it will cause motion to occur. It will cause the current carrying conductor to move. If I have a wire inside a magnetic field and I cause motion on the wire, it will cause a current to occur. And the last one, these two aren't really linked, but if I have current at all, it will generate a magnetic field. So these three concepts are closely related, and you'll see why in just a second. But let's move forward with these learning objectives. So first one, here we go. Let's move forward with these learning objectives here. The first one. So the first one here we're going to talk about is, let me just bring it up. So that, there we go. Make that visible for you. Okay, so show an appreciation that a force might act on a current carrying conductor placed in a magnetic field. So this is a really simple one. Basically, anytime you have a magnetic field and something that conducts electricity, normally a wire, you will cause motion in both the wire and the magnets. And so I'm going to draw that for you. So pretend here we have our magnets here. So there's my north pole, and here's a south pole, and this can be like maybe a horseshoe magnet, so it'll be connected like that. But you know, it can be any magnet of any kind. So here we go, we're south pole magnet, and I'll have a magnetic field going across the poles. And over here, I will have say a wire. There has to be a particular direction, but if you imagine the wire, if I do an ISO view going across like that, so this is towards you, and this is away from you. So this is actually coming out of the screen right now, but if you can just imagine that. And what will happen here is this will actually cause the wire to move. And you can try this at home if you want. Basically, grab a piece of aluminum foil, grab a permanent magnet, and run a current. Connect the aluminum foil to the poles of a battery, and you will see that the aluminum foil actually moves. If you have a strong enough magnet and current. So this is called the motor effect, and to explain this, it's just kind of the interaction I was talking about before. So any current carrying conductor in a magnetic field will experience a force, and it will kind of experience a double force. So if this moves down, it will cause the magnet to move up because, you know, Newton's laws, every force has an equal and opposite reaction. So let's take a look. So the magnetic field is acting on the wire to pull it down, and then the wire therefore is acting on the magnet to pull it up. So here we go. But normally what you get is this magnet is normally quite heavy, and this force acting upwards is normally negligible compared to gravity. So you don't really notice it, but it is there. So how do we know which direction the wire moves? Does it move up, or does it move down, or does it move left or right? This one here is, the kind of grand formula for magnets is this. The force, which is a vector, is equal to the charge, which is a scalar quantity, times the velocity of the charged particles, which is also a vector, cross product, this isn't times, this is cross product, with a magnetic field, which is magnetic field density, which is also a cross product. So, you probably have done this in class, but you just didn't realize you were doing cross products because the Cambridge course doesn't really explicitly say that you have to know this is a cross product. But I'm going to just quickly explain what this means. A cross product, the definition of cross product basically means that the magnitude of F will be equal to the charge, which is still a scalar quantity, it doesn't really matter, times the magnitude of the velocity times the magnitude of the magnetic field times the angle between them, the sine of the angle between them. And the actual one, if I didn't do the magnitude, it will be times a little unit vector there, which changes direction. So basically, this would be there if I wasn't talking about magnitude. So the magnitude is times all these things. Is basically the charge times velocity times magnetic field times the sine of the angle between them. And the actual vector, the force vector, is the same thing, except it's also times the unit vector. And what this unit vector does is it changes the direction. So this, what you get is when you cross product two things, you get a third line which is perpendicular to both lines. So if this is my first vector, so if this was V and this was B, my third vector would be there. That would be my F. And this one here is actually perpendicular to both these. So I'm going to go ahead and clean this up and try to explain that a bit better. Okay, so the reason we have the sine theta in is because you're always looking at the magnetic field, which is the component of the magnetic field acting perpendicular to your field. So here we go. If this is the current here, imagine that's a wire with a current running along it, and the magnetic field is coming at an angle like that. What's going to happen is you actually only want the magnetic field, a component of the magnetic field. So if I go ahead and you're actually wanting this one here. So what you have to do is it's a component of this, and there will be an angle between. There will be an angle here between an angle which exists between the magnetic field and the current. And basically, the value of this component is whatever magnetic field is times sine theta. So hopefully that explains why the formula is how it is. Anyway, that's really not all that important. So basically, how do we know which direction the wire moves? Does it move up or does it move down, or what really happens? So what you have to realize is it will always move in a third direction. It will always move anti-parallel to both other forces. So if that was the current and that was the magnetic field, and so if the current was going straight up on the page and the magnetic field was going straight across the page, your movement would have to be either straight into you, towards you, or straight away from you, into the screen. So it have to be one of these two. How we know which one of these two? There's a lot of ways to decide how. A lot of teachers teach it differently. Some learn something called the Fleming left-hand rule, but I have kind of made it my own rule. So you can, if you can't understand me, you can go search up this Fleming's left-hand rule, and it's quite simple. Actually, I'm going to go ahead and search it up because I'm quite shocking at drawing hands. Okay, so basically, how do we know which way the wire is going to move? We use Fleming's left-hand rule, and I'm going to bring up a picture of it right now. So here we go. This is Fleming's left-hand rule as a little picture I just took off Google just now. Hopefully it doesn't have any copyright on it. You make the shape of your finger there's three directions, which is basically, you can see that all of these are perpendicular to each other. And basically, you take your two fingers and you point your index finger towards the direction of a magnetic field, and you point your middle finger in the direction of a current, and the direction of your thumb will then be orientated in the direction that the force will be, the wire will move. So if I just move this along, say here, and I'm going to draw some pictures and hopefully show you that this does work. Okay, so let's just draw some, just see some examples. So if we have here a magnet, and there's the north and the south poles, and so there's the magnetic field going across, and here we go. Let's go for a wire going like that, and the current going that direction. Remember, this is the finger points in the direction of the current, not in the direction of the movement of electrons, so be careful. So there's the direction of current. So if you kind of just orientate your finger right now, your index finger pointing left to right, and your middle finger going straight down because that's the direction of the current, and where will your thumb be pointed? If you got it right, your thumb should be pointed straight towards you, out of the screen, and that's the direction the wire will move. It will kind of bend out towards the screen. Experience a force. And what's really important is this force is only experienced between this region here, between the region that's inside the magnetic field. The regions of a wire outside of the magnetic field won't experience any force. So if we take a look on a side view, the wire would kind of deform to look like that because of the force it's experiencing that way. Fantastic. Okay, so now that's an appreciation. That's more than an appreciation, in fact, of why a force might be covered. Sometimes I will go beyond the syllabus a little bit, just so that, because I really believe that you need a really concrete understanding of things if you want a good mark. So let's move on to point B. Okay, point B here. So recall and solve problems using F equals BIL sine theta as interpreted by Fleming's left-hand rule. So we just saw Fleming's left-hand rule, so we already know which direction it's going to move. Now what we need to know is what the actual, what's the magnitude of the force? What's the force going to be on the wire that's, that's being acted on this magnetic field? So this is when we get our numerical questions. So I'm going to quickly derive this for you, why it's F equals BIL sine theta. So we saw before that it's, the formula is F equals Q times V times B. Cross product B, sorry. Okay, so what do we know V is? V is essentially distance over time. Distance is a vector, but time is a scalar quantity. So what happens if we can just take this time and move it along to there, so that's distance over time, and we'll take this distance and move it and replace this V. So there you go, it's the same formula as it is right now, right? So what do we know about charge over time? What is charge over time? It's, of course, current, right? Here we go, current. There's some debates whether this current is scalar or vector, but we'll call current a scalar quantity because you don't ever have negative 3 amperes. So here we go, we have current times distance times this. And what do we have here? F equals BIL, F equals ILB. That's the same thing, right? And what do we say we define cross product as? Cross product is essentially, as I said before, equal to I, and here we go, it's the magnitude of L and the magnitude of B, which is BIL, times sine theta. Sorry for my terrible handwriting. And also in a unit vector in a different direction, times the unit vector in a different direction. If we're looking at we're looking at magnitude now, but it's also, but it's actually times the unit vector in a different direction. So that's for Fleming's left-hand rule. But all this does is change the direction of a vector. So this is why it's F equals BIL. So let's do a let's do an example, and you'll be able to quickly see it's a very, very easy formula, in fact.